welcome back. So in our last class we talked about definite integrals and how the definite integral calculates the area under a function and above the x-axis. And we saw as kind of the opener for last class an application of why we might care about area under a curve. And what we saw was that if we have a graph of a derivative, then the area under that derivative tells us about the total amount of whatever the thing is. So today what we're going to talk about is we're going to look at a few examples of applying this idea of area under the derivative. And our first example, we have the rate of depreciation of a building is given by d prime of t equals 3,000 times 20 minus t dollars per year, where t is between 0 and 20. So our model only is valid for from 0 to 20 years. And our job is to find the total depreciation of the building over the first 15 years. Okay, so the first thing we want to do is we want to graph our derivative. So our derivative is d prime of t equals 3,000 times 20 minus t. So we're going to head over to the computer and look at our graphing calculator emulator. And so we're going to type in our function. We have 3,000 times 20 minus t. And then for our window, we're told that our t values are between 0 and 20. So we'll look at 0, an x maximum of 20, and then I'll use zoom fit to figure out what the y values should be. Oops, too far. Okay, so here we have our graph. It's a diagonal line. Just to double check here, in our window, our y minimum is 0 and our y maximum is 60,000. So the fact that our y minimum is 0 tells us that our graph is showing us the x-axis along the bottom. Okay, so, and the other point here is that this graph crosses the x-axis at an x value of 20. Okay, so let's draw this picture over on the board. Okay, so our graph was a diagonal line, and the graph crossed the x-axis at 20, so I'll mark here 5, 10, 15, and 20. And t in this case represents years, so along our x-axis we have years. And our y-axis is representing the rate of depreciation. And that is measured in dollars per year. And what we saw on the graph on the computer was that the top corner of this graph occurred at 60,000. So this says that at time 0, when the building is first built, that you should expect that in that first year, the building is going to depreciate at a rate of $60,000 per year. And as time moves on, that rate of depreciation is decreasing, which means you're losing less money each year as time goes on. Okay, so we are asked to find the total depreciation of the building over the first 15 years. Oh, and I guess I should label this as y equals d prime of t. Okay, so we are asked to find the total depreciation of the building over the first 15 years. So what that means is here's our rate of depreciation, that's our derivative, and we want to find the total depreciation. So we want to find the area under our rate, under the derivative, over the first 15 years. That means from year 0 to year 15. And we want to find the area in this region right here. Okay, so there are a couple of ways to come up with this area. For one thing, in this particular example, our function is a diagonal line, which this shape then becomes a trapezoid, and there's formulas for finding areas of trapezoids. And if you're taking an accounting class, it's possible that you might come up with this area by finding the area of a trapezoid or some other formulas that give you this value. This idea of depreciation is important when it comes to taxes and things like that, because you want to know how much do your rental properties depreciate over time, over the year, so you can take tax credits and things like that. Okay, so we want to find this area. Again, because this is our derivative is a diagonal line, we could use some kind of geometric formula on this. But we're going to want to be able to use this idea more than just for diagonal lines. And so another way to think about this area under the curve is what we talked about last class, which is the definite integral. And so our total depreciation over the first 15 years is going to be the area between 0 and 15, so the integral from 0 to 15 of our derivative, which is, let's see, 3,000 times 20 minus t dt. So if we can evaluate this integral, then we'll come up with a number. Okay, so I look at this definite integral and I ask myself, how do I evaluate it? And the first thing I do when I have a definite integral is that I ignore the bounds, which make it the definite part of the definite integral, and I look just at the integral of 3,000 times 20 minus t dt. Okay, so now what I notice here is that I have a set of parentheses. And usually when I have a set of parentheses, that says I'm going to want to do a u substitution. Now the thing that's a little bit different here is there's no power on that parenthesis, which means I can actually get rid of those parentheses and avoid having to do a u substitution on this problem. And I think that's a good idea. So instead of doing a u substitution, I'm going to distribute this 3,000. If there had been a power up here, I would not be able to do this. Okay. So we have the integral of 3,000 times 20, so that is 2, 3, 4, so that's 60,000 minus 3,000 t dt. Okay, so now I'm ready to find my antiderivative. The antiderivative of 60,000 will be 60,000 t. Now, you might have thought to say 60,000 x. The reason I know to put a t there instead of an x is because of that dt at the end. That tells me that the variable I'm using is t rather than x. Okay, so now I have minus. I'm going to add 1 to the power, so I have t squared. And then I have 3,000 over 2 in front. And then I have a plus c. Okay, so I can clean this thing up. And I have 60,000 t minus 1,500 t squared plus c. Okay, so we found our antiderivative, and the part of the antiderivative that we care about is everything except for the plus c. And so this is our capital F, our antiderivative. And what we want to do now is we want to plug our x values, our t values, our bounds into our antiderivative. So our top bound is 15. So we have F, capital F of 15 will be 60,000 times 15 minus 1,500 times 15 squared. And when I type that into my calculator, and I did this ahead of time, I come up with 562,500. And the next bound I want to plug in is the bottom bound, so I plug in 0 into my antiderivative. And so I have 60,000 times 0 minus 1,500 times 0 squared. Well, that's all 0. So I plugged in my top bound, I plugged in my bottom bound, and so now I have capital F of 15 minus capital F of 0, which is 562,500 minus 0 is 562,500. Okay, so we just found our number. This number, which is roughly 500,000, says that the area under our function, under our derivative, between 0 and 15, is equal to 562,500 as an area that's square units. But in terms of our particular example, let's talk about what this value means and what label should go on this value. Okay, so when I think about the label, well, this number in here is an area, and typically area, at least area of a rectangle, is base times height. Now, our base is being measured in years, and our height is being measured in dollars per year. And if I multiply these labels together, the base times the height, the X label times the Y label, then the years cancel, and I'm left with dollars. And so what this tells me is that this building has depreciated by $562,500 during the first 15 years that it had been built. So this building depreciated $562,500 over the first 15 years after it was built. Okay, so we were given the derivative, we were given a rate of depreciation. We found the area under that function, and the time interval we cared about was time 0 when the building was built up to 15 years later. So we found the area under the derivative between 0 and 15. We calculated that by evaluating a definite integral, and the answer we came up with, we could label by taking the base label times the height label, years times dollars per year, gives us dollars.